Okay, I'd like to talk about an aspect of time domain computing that's a little different than what's been talked about up to now. And I'm really coming from the sensor direction, from the sensor end, so not the front end simulation science end. But there's a revolution going on in the sensor technology, in the data volumes. Extracting information out of these massive data flows is going to be a tremendous problem. And now, what's really getting interesting in the time domain astronomy is pushing it down so that the time scales we're looking at are measured in seconds and minutes, not hours and days. And that changes the way the game is played. And this is really going towards what's going to happen in the LSST era and so on as we push down and go in those new directions. And this business is really a regime that has to be attacked with robotic instrumentation. You cannot have enough graduate students that are fast enough with good enough attention spans to really pull this off. There'll be huge numbers of transients. It's really the land for machines, automated discovery. And one of the huge challenges will be the triage, that when these huge numbers of transients start coming through, how do you recognize the important ones and get on them in real time and interrogate them to get the information out that you need to do this, to address the science? We can't really do this forensically. There'll be signals that are missed. You really want to be able to get on, recognize what are the important parameters to observe, and observe them, and do it in a coordinated way so that you can extract all that information. When you get in this regime, of course, there's so many transients, and the resources you have to follow them up is you can very quickly get into essentially a denial of service attack. That there's so much stuff coming in, so little coordination between the instruments, that you're basically paralyzed, that most events won't be followed up. So how do you build modern instruments that can address that sort of thing? And I claim the way to do it is to, well, let me say, here's where we are now, before we go to a way to do it. So we're already measuring things where seconds matter, and that's in gamma ray burst follow-up. But the way we do this is like second grade soccer. If you know what second grade soccer is like, everybody just sort of pounces and kicks at it. That's pretty much how we do gamma ray burst follow-up, and when it's all over, you look at what happened and trying to piece it together. That can kind of work in small number, one soccer ball. But now put 10,000 soccer balls, only one of which is the important soccer ball, with no coordination. You can see the result. Not much will happen that's effective. So how do you deal with that? So part of the way we're going to deal with that are some of the things that Josh Bloom talked about this morning, is characterizing the transients to recognize which ones have which properties and are the best ones to follow up. Now, the best one to follow up may depend on what kind of science you're looking for, of course. There won't be one best transient every night. There'll be a few transients in each subject area that are the interesting ones to follow up. So how do you coordinate that? How do you make sure that you're getting the right assets to follow those interesting ones up? And how do you coordinate that? Now, right now, the way we do it is you send an email out or you call your friend up on the telescope. That won't work in the future. Well, that will still work for a small number, but it won't work effectively for the massive number of events we're going to have. So we've got to build new sorts of systems, and we're already building these, is to put distributed artificial intelligence within the systems to be able to coordinate between various sensors in real time to optimize the follow-up and the response. So the picture we're talking about is, just imagine you have a broker, and not in the computer science sense, but in the E.F. Hutton sense, if you will, of here are the interesting transients for you. Then coordinate that so that you can follow up those interesting transients. So the broker on the front end spits out what are the most interesting things that are coming in real time. Then you have to a way to coordinate the whole follow-up. And that's one of the things I want to focus on here. So there has been work done on these systems in artificial intelligence, and sort of the two poles of these systems are, on the left-hand side here, a distributed computing problem, where you had identical nodes that are spatially or temporally even distributed, and they're controlled as slaves from a central controller. the other extreme, the other pole in this, is multi-agent systems that go out and work autonomously. There's no real goal coordination, and you sort of have a competition between agents to get the best response from that. What we really need is something in between these two poles, where we have heterogeneous assets out there that can be coordinated to optimize the follow-up, all working together. So that's what we're aiming towards. Here's a system we have now at Los Alamos that we've built. These are all telescopes working together in real time. And what it basically works as is we have full sky monitors that do persistent surveillance, recognizes interesting transients, and cues follow-up in seconds of other fast response telescopes. And of course, we get events from things like spacecraft, like the SWIFT mission here, to other sources of transients. And in fact, we're about to do LIGO follow-up and things like that with these systems. The architecture we've come up with is called a dynamic coalition architecture. And the way this really works is that each sensor in the system has an agent working there that's looking at its own best interests, and it's being asked to enter a coalition. So right at the broker, broker assigns a manager of the coalition. The coalition starts this follow-up, sends out messages to all the sensors out there. They recognize whether or not they want to be in that coalition. The manager decides whether or not there's sufficient interest to do that, and then starts the coalition. So you can see this is a way to make sure that you coordinate, you assign roles, like in the soccer game. If you join this coalition, we're going to ask you to play this role to make this kind of observation at this time, and get that person to follow up, get that. And so the agents can be, mostly they will be machines, but in fact you can imagine that could be a person that looks into a database or does some calculation even or something like that to enlighten the whole follow-up activity. Can turn it out into block diagram. I won't go into that, but basically the idea is that you have this control, this coalition manager that's communicating with these agents that represent each one of the different assets, tries to get them to enter the coalition, and then decides on how to manage that coalition. So the other aspect of this is, what's an optimal follow-up? How do you do that? So at these early stages, what we're using is case-based reasoning. And case-based reasoning is very simple. It's, I think this is likely to be an object of this type. There's a recipe for how you follow up to interrogate an object of that type. What are the observations you make? Sort of go down the list. If it's this kind of object, it should have a changing light curve that looks like this, or it should have a color like that, et cetera, et cetera. Recognizing whether or not that object is following. So you go down that list. It's trying to decide, is this really that particular kind of object? And dynamically, as the more information comes in, deciding what's the next key observation that needs to be made. This allows us, these recipes, to bring in humans to give information to the system. So you go out, you perform according to certain case, a recipe, if you will. Do that follow-up, and then the next day a human comes in and says, well, that didn't look so great. If only we would have done an observation in this way. And you can update that case to optimize it. And you can see you can subdivide into separate, different types of cases for different objects. And it's all done dynamically. It can be done on the fly as the program evolves. This is just a flow diagram of how these things we're building work. But the main thing is that it's designed to efficiently make sure that you get the right observations you need from the right places. And it pushes the responsibility for information about the sensor to the people that own the sensors, if you will. They don't have to give you all the capabilities of their telescope all the time, you know, what state, what they're looking at now, or so that you can help optimize this particular follow-up. But one thing that you do have back at the broker are sort of the ideas about where the place is, how fast it can respond. And another important thing is how reliable has that instrument been at collecting the observation. So this is kind of a trust model, if you will. It's almost like eBay feedback or whatever. You've been invited into the coalition. The telescope was supposed to perform certain observations, and it was successful or not. You use that in ranking for key observations to have a feel for who can perform the kind of observation you need in real time. So this gives you an idea of, you know, if you go back to the soccer analogy, this person's a very good forward, they can score all the time. This other one's not too fast, not too good, would be a lower priority for bringing into the coalition. Another thing that will happen with the agents is, of course, everyone who owns a telescope has priorities for that system. They recognize what are the important kinds of things they need to do with that particular asset. So they can decide how to optimize the return from being in the coalition. You know, whether or not they want to join that coalition or not can be very much dependent on what their priorities are for the system. I mean, this can go to national telescopes and so forth, figuring out priorities of various programs, and et cetera. All those things are things we're going to need. And you can see the kind of questions that the software will ask and will be tailor-made at each one of these places as to what kinds of observations they will enter into. So the important point about this is that it helps you get away from not just always going to the most powerful instrument you can think of. That we won't be able to go always to CeC or always to some powerful telescope, but you want to recognize what are sufficient assets to return valuable information scientifically. So when you have a heterogeneous system of assets, how do you optimize that? How do you get the best scientific return? This is how you do it on this sort of approach. So this is sort of a distributed instrument idea, but there are distributed, of course, computing ideas that work similar to this, you know, cloud-type ideas and things like that. This is what we're trying to bring to the sensor side of the house. So I think the main takeaways I want you to have from this is we really are entering this era where this kind of infrastructure is going to be essential on the observational end to really return scientific results that are important as we go to very fast transients. These follow-up schemes that are going to employ ecosystems of telescopes and instruments will be extremely important in this new regime where we get thousands of transients a night that have to be followed up. And this multi-agent approach, this dynamic coalition architecture, I think is a way that can really optimize those returns and really standardize and help us develop a way to enable this sort of follow-up. The key piece that still needs to be developed here is the whole international collaboration of standards and so forth. So we've developed standards for VO event and so forth of passing information. We've not yet developed standards for how you do the agents, how you intercommunicate between the agents, how you transfer that information around in real time. I think I'll stop there, yeah.